Also, good morning, our audience. We are students from the DRL. My name is Valentina, and with my teammates Leo and Florencia, we are within the studio. We are responding to Studio's Propolis brief, which is elemental, and we are studying natural phenomena as a form of technology to sustain life. And since our early studies, we've been studying fluid phenomena as a way to think architecture as a form of technology. And fluidity doesn't make any distinction between granular particles or liquid particles. So we've been studying different ways where we can influence how matter behaves and organizes over time. So for example, here with sand fluidization, which is basically this fascinating phenomenon of sand behaving like a liquid when air is forced upwards in a bed of sand. And with this, we could influence how a granular material that lays dull in a bed of sand can start to have a dynamic and fluid behavior. To also the study of fluid particles with this viscous fluid that is silicon oil. This is a quantum mechanic analog in the fluid world, which is basically trying to represent this pilot wave theory, so the duality between particle and wave. And this particular phenomenon is very interesting for us because it has some particular organization, very legible logic of organization, and interactions that evolve over time. So for our first studies of granular solids, we were trying to see how we could create a material displacement. This was a much more analog kind of prototype that fed up into this idea of, okay, maybe we can start to design machines that we can program and create a choreography of matter. So this board was fitting this sand tank. That it was a very interesting experiment because it proved us wrong in many ways. We thought it was going to be much more easy to create this material displacement. But the reality proved that we had to design too many nozzles and test many different angles in order to get that patterns to start to show up. So all the way from 90 degrees to 0 degrees, we started to test also this horizontal push that had a very different kind of behavior. We start to see that with loss of gravity, we start to, well, actually, we're not now influencing the material against gravity. So now we see much more how the angle of repulse is starting to show up. So we also tested this digitally with some simulations of vector fields, trying to see how we could displace this within the material digital world. Again, influencing how granular particles can be displaced. And we also always envisioned this system as a closed-loop system, so thinking that we could change the material behavior from fluid to solid and go back again. So the way that we did this, we explored these arresting particles, was by introducing a binding component, which was salt. Always with this idea that if we bind sand with salt, then just with water, sand can always return to its initial state. So these were some of the tests that we did. First, we started with salted water solutions, and then we thought, what if we can erase the water out of it and just melt salt? So this was some of the results that we got. And we also did scaled-up version with our teammates, just to see how things we could go with this experimentation. But we never saw this as creating structures, for example, in the desert, is something that can be easily drawn to. But we saw this more as an experimentation, how we could influence the behavior of material in playing with material in its different states.
Cool. And along with solid particles, we also studied the behavior of liquid particles. So when you have a fluid of a certain viscosity and you place it on top of a vibrating speaker, we can create these liquid particles that bounce indefinitely. So we're using silicon oil here. And the two parameters of control here is frequency, or the rate of vibration, and acceleration, which is the force of each vibration. So when the acceleration exceeds a certain threshold, you get standing waves or Faraday waves on the surface. And testing different depths and also different frequencies, you get different kind of scales of patterns. Generally, the lower frequency, you get bigger patterns, and higher frequency, smaller, more dense patterns. And the bouncing droplet starts to walk around the bath when the acceleration is increased. And this is us tracking the motion of the droplet over 15 minutes. And one fundamental principle or feature of this system is a particle-wave interaction. So the particle creates a wave field every time it bounces, and its trajectory is determined by the wave field from its previous bounces and from the other particles. And so the logic of this organizational system is through wave interference. And these are two droplets kind of interacting through their wave field, and the wave field is locking, so they maintain this uniform spacing between each other, and they orbit. And also scaling up with multiple droplets, their wave fields interact, and which inform their organizations. And at different frequencies, the wave fields are different. So at 40 hertz, they kind of organize into a lattice structure, and at 140 hertz, they have a packing organization. So kind of utilizing this, we can, by varying the acceleration and the frequency, we can control the distance or the spacing between the particles. And this is a multiple droplet example of this pulsation behavior by varying the acceleration. And also altering the frequency or having two different frequencies that slightly out of phase each other, it can also create this kind of pulsation or similar behavior. And just how we're working on this. So it went from a single speaker to something that's much more precise. So we have a base so that we could level the kind of bass completely level, and also having a black background underneath the bass helps us visualize it, and also a new way of introducing the droplets without disturbing the wave field. And also to digitally simulate this, it kind of can be broken down into three parts. So we have the vertical dynamics of the droplet, the wave field it creates, and also the horizontal trajectory. So just having a peek behind how we're doing this. So we're kind of implementing mathematical models from existing research. So the vertical dynamics is informed by the impact force and the gravity force. And the horizontal dynamics, or the trajectory of it, is dependent on the slope of the wave as it bounces. And the wave underneath the droplet is modeled through an equation that calculates the height of each point on this mesh surface over time. And those equations took 2 months to understand and implement. And now that we have it implemented, we can start seeing kind of the different organizations and test this algorithm without the physical constraints. And this is one example of the test. We could kind of be very precise in where the starting points are for the droplets and see what the differences are. And they organize, in this example, into these, the wave fields lock in this example. And we're still in the progress of testing this algorithm further.
So if we were studying this fluidity in two starting materials, so granular solid sand and then viscous fluids with silicon oil, we started to think about how we're going to apply this wave logic and all the knowledge we got over these past months into something that can be much more readily available as water. So we are starting now with our frequency tests with water, with this ambition to see, not losing the concepts that we had before of the wave organization, wave-particle duality, but seeing the silicon oil experiment as our 100% control kind of experiment, and then losing some of that control and letting the inputs to influence the matter in a different way. So within the lab, we experiment and we try to push this idea of architecture as a form of technology. At the moment, we're still thinking how this knowledge can be applied, but we do see that this can be, so rather than having static and fixed infrastructures or influences in the environment that are static, and actually all the problems that we're trying to solve are dynamic and evolve. So the idea it is to find a new model or way to engage with our environments, to let the landscapes to adapt and evolve over time. Thank you.
Should we discuss it?
Yeah, okay. We have time. Yeah, we have time. Maybe we can have this.
It's very impressive. I think the presentation was great, but the difficulty of what you've taken on mathematically, I think, is really impressive that you've been able to come to a kind of definition of that. The application, it would be a shame in a way if you just take this as a kind of way of organizing a network or a mesh systems on the landscape. So there are landscapes that incorporate both particulate matter and viscous matter. And these salt marshes and places like that. And they're very interesting environments that are more or less on the edge of what is currently inhabitable. But we are going to see a lot more of those over the next 50 years. So that climate change is making those kind of environments spread. Some highly saline, so that, and we don't know, and maybe Rachel can comment on how these kind of beginnings a way of organizing material dynamically through these kind of systems would affect microorganisms and so forth. And one of the strangest new environments is where the permafrost is melting. So very high biological content, much of it quite ancient, that's preserved and comes to life when it warms up. Very high gaseous environments that are beginning to be where the methane clad rates and things are beginning to penetrate through. Yeah, go for the weirdest, strangest environments that have some of these the properties that somewhere near what your initial experimental properties are. Do you want to add anything to?
Yeah, I'd love to. I'm so excited when I see experiments like this. I think that the kind of hands-on investigation of the weirdness of matter, I think, is exactly where we need to be. And I am also impressed by an attempt to mathematically describe, but also I think that you've got a beauty in that kind of the slippage between the edges of what you can actually describe. You kind of have to stay with the difficulty of what it is that you're observing and kind of understand that you don't understand it all and possibly never will. So there are a couple of elements within what you showed that I would, let's say, maybe suggest you do a few more maybe tests. So one is to agentize because at the moment what you're doing is you're agentizing the field, right? Your matter is relatively inert and you're using it as a pinpoint, it's, like a pixel, to see what happens when a field becomes unstable. And that's really fascinating. But, I don't think you need to worry about whether you can describe it or not. But if you, for example, used a medium and a droplet that consume each other, so for example, the ones that I was exploring was like an alkaline environment and a fatty droplet, then the fat interacts with the alkaline environment and it starts to produce matter, a soap. And then that changes the mass of the droplet. It starts leaving traces and just stuff that is totally undescribable, mathematically, as far as I'm aware, starts happening. And it starts to show you interface disruptions. And interfaces was where you can actually start situating things. So at the moment, you've got everything vibrating. It's energetically very heavy. But if you can figure out how your droplet and field start to exchange things, I think you'll start to uncover stuff. And I won't be able to predict it. You probably won't be able to predict it. But you kind of have a look to see what you can do at the interface level. How can you charge up those particles? I only mean as a material, so that they have a slightly different relationship than the kind of passive indicator that they're currently doing with the field. So the more agency you can get in those droplets, the better. I mean, even do a Gordon-Paskin, try some, paramecium or something, kind of have, or some, a biofilm, or, have a look at different kinds of agents. I think you've set up your question very well. I think biofilms might be interesting because obviously microbes try to stabilize themselves against these perturbations. So we're going to go to microbes now. And what they do is they use soft structures, right? So there are different kinds of biofilms. So the ones that we would recognize in the kitchen sink are productive biofilms, where the microbes can literally thrive indefinitely, grow indefinitely, providing they have enough food. And so they have this wonderful little life cycle where they kind of start off colonizing a surface, then they grow thick and fat, make all this matrix, and it comes to a point where there's overcrowding, so they start shooting off bits of biofilm to follow the stream of direction and then go settle somewhere else. So that's a very interesting kind of biofilm dynamic. There are loads of pictures online that you can get to have a look to see how replicating matter starts to settle perturbations or changes in environment. But then there is a kind of a more stable biofilm, which normally is associated with an electrode, and that's because like microbes like Shewanella and Geobacter, they don't need carbon. They can eat and poop electrons, so they need to form a very, very thin film around electrodes. So they'll stay static even when everything else is changing. So what you've got in terms of looking at different biofilms are different strategies for occupying space. And so these are very primordial questions. And then in terms of mineralization, once you've got soft matter being excreted to, let's say, dampen down environmental perturbations, it then will start to catch the sand particles that you were working with earlier, and then you kind of get a biomineralization. So you've got some wonderful dynamics that you don't have to do all of it, but having a look at a system that has a logic that goes beyond the passive pixel or indicator, I think will help you start to think about the question that Mike then was addressing, which is, so what do you do with this knowledge in terms of an architectural context? And I just want to, I'll be very keen to hear what other people have got to say. But two examples I would give you. One would be the city of Venice, which is exactly on that salt marsh that Mike was describing. So the way that Venice was stabilized was with wooden posts to kind of push through the silts. So I was looking at the liquefaction or the liquefaction that the sand was undergoing. So that would be an ancient process to kind of make the body stickier, kind of spikes, those kinds of things. But are there other ways maybe that the salt marshes could be congealed? Or, could you have a dynamic situation where if the waters rise, that Venice floats, and then as it, as the waters recede, it kind of sticks like a biofilm back into the salt marshes. Maybe there is an association with things like trees and floating balsa wood, kind of materials. But I think you've got a kind of a lovely kind of dynamic foundation for a settlement there, which I think could be done from first principles, drawing on the kind of work that you've been doing. And then the next one, I think, is the dramatic change in climate. So what we've seen recently in Valencia, when water and soils and everything becomes liquefied. So what happens then? Look at the streets of Valencia and you've got cars just piled up, like trash. So I think that there are limits to how the liquefaction and kind of reconsolidation takes place. And so also with the same with Venice, there's a point where things settle, there's a point when things disperse, and then things coming back together again. So whether it's permafrost or mud flats or areas that are flooded, I think you've got a lovely system here, but I think you need to agentize your particles and think about interfaces as to how those particles can now start to forge and undo links with the energies and the movement that's around them. But I think this is fascinating work, and I'd be really keen to see what you do next.
Thank you.
If anyone else want to say something about this? No? I just want to say something very along the line what Rachel said, which the principle that you're working with, displacing matter, maybe this could, because this is something that, again, that the example of Valencia and permafrost, matter will be displaced regardless of what we do. Maybe you, when your experiments and what you're building upon could actually facilitate this phenomena happen in more controlled way that does not necessarily go against the way of living, displacing matter. It's a far-fetched idea because from the scale of your experimentation until the scale that we can think about our architecture is still a long way. But the principle itself, displacing matter, but in a controlled way, could be a very interesting experiment, could be a very interesting research stream to explore. I mean, regardless of the context as your thesis or in the future research endeavors, I think this is quite interesting to think about it. Yeah, thank you. Thank you.